So yes. So the z-intercept is 6 also. Right. So that's going to give us the following surface over here, and well, when we take the partial derivative, okay, let's take the partial derivatives first. So that's partial of z with respect x, which equals -1, and partial of partial of z with respect to y, and that equals to -2. And well, what's the, okay, set up the integral, double integral of, okay, I need some space here, yeah, that's fine. Over s, xy ds, notice it's not just a 1 in the integrand, that's d big S, and that's going to be the integral, or the double integral of xy, and let's write down the element of surface area, which is the partial of z with respect x quantity squared plus the partial of z with respect to y quantity squared plus 1 dA in this case, all right? That ds becomes dA when we introduce that element of surface area. And well, let's just substitute what we got for our partials. So that's going to be xy square root of -1 squared plus -2 squared plus 1 dA, which is going to be, well, actually, yeah, that's fine. That's that becomes r now. And xy square root of, okay, that's a 1 square, which is 1, plus 2 square, which is 4, plus 1, well, that becomes a 6. That adds up to 6 dA. Okay? Well, let's iterate the integral. And I'm going to go dy dx. Hopefully it works. And again, we need to see what's going on in the shadow here. So that's the projection onto the xy plane. All right. And well, so that's going to give us the following graph. That's this line right here, for which the x-intercept is a 6 and the y-intercept is a 3. Well, so in this case we have this equation of a line, which is y equals to something that has a y-intercept at 3, and a slope of dive 3 run 6, it's essentially -3/6, which reduces to a -1/2 x. And well, for the limits of integration with respect x, well, that's going to go from 0 to 6. Oh, I mean, oh yeah, 0 to 6. So from 0 to 6 in the x direction, and from 0 to -1/2 x plus 3. So that's the setup of the integral, and evaluating this integral should result into 13.5 root of 6. All right. So we're going to solve this problem in a different way, and the setup, well, it's going to be pretty interesting. So essentially, we are going to rework the whole thing, the whole problem. However, instead of projecting, as we usually do, onto the xy plane, we are going to project onto the yz plane. And instead of using a function z that depends on x and y, we will use a function of x that depends on y and z. And we will find out how it's actually going to give us the exact same result. How are we're going to set it up? You'll see how it's going to work this time. So I'm going to do the graph in 3D again. So that's and what did we get over here? Okay, so that was it was 636, 6, 3, and 6. That's one. That's another one. Same tetrahedron. However, no, we're not projecting onto the floor. We're projecting onto one of the walls. That is the wall that involve the y-axis and the z-axis. So in this case, let's shade that that wall actually. So we're going to project it over here instead. So in this case, well, let me label the intercept. So that's a 6, 3, 6. So we're going to look at the projection onto the YZ as opposed to the X and Y. So that's X, Y, and Z. All right. And I'm going to look at this individually, this wall, and I'm going to project it over here. So that's going to be, first of all, the z-axis and the y-axis, no more the x-axis and the y-axis this time. So this will be 3 units and 6 units. That's going to give us the diagonal line over here. All right? So that's going to be our region. Well, let me shade it with the same color. Honor that. The setup is going to be a little different. We're going to have this little pitfall we got into in the previous example, not in the previous part actually. You'll see how this going to work. Well, so in this case, we need to define a function of y and z. So again, I'm going to refer to the original equation that I have. Well, I'm going to write it in terms of the equation of a plane. That is x plus 2y plus z equals to 6. Even though we were given the equation already solved for z, so I'm going to move everything back. But in this case, I'm going to solve for x to obtain a function that depends on y and z only. And so in this case, well, the two partial derivatives that we're going to, okay, let me set up the formula first so you can see, so you can get a better visual in this case. So double integral with respect s of x of y ds, big S by the way, and double integral of x, y, square root, in this case, well, that's the partial derivative of x with respect y, quantity squared, plus the partial derivative of x with respect z, quantity squared, plus 1, dA, over the region R. All right? So in this case, essentially, this is, instead of saying z subscript x and z subscript y, essentially we're doing, check this out, we're doing x subscript y and x subscript z. That is the partial of x with respect to y and the partial of x with respect to z. And what's next? Okay, so let's take those partial derivatives. That is x with respect y, that's a -2, and x with respect z equals to -1. So, same color. That's equal to the double integral over R of xy square root of -2 squared plus -1 squared dA, where in this case equal to the double integral over R of xy square root of, okay, again, I'm forgetting a 1. That's going to be another 6 again, right? And in this case, notice dA, well, it usually was dy dx. However, we're not working with functions of y and x this time. We're working on functions of y and z. So in this case, I'm going to go the order dz dy. But do you notice anything weird on the integral? There's an x in here. We need to get rid of that x by writing whatever x in terms of y and z. So that's the integral. I'm going to leave space for limits already. And so that's x, which is in this case the function 6 minus 2y minus z times y square root of 6 dz dy. And well, let's look at the limits of integration. We already have the projection onto the YZ plane, and onto the XY plane. And, well, let's get this equation. So we have an equation, y equals to, well, the y-intercept is 6, and the slope is, well, dive 6, run 3, that is 6 over 3, or negative 6 over 3, rather, that's actually negative 2x. So we go from 0 to negative 2x plus 6, and in this case from 0 to 3. Hmm? Yes, that's what I meant. Yeah, the 2y, yeah, that's true, thank you. 2y plus 6. Mm-hmm. And well, evaluating this integral, yes?
Z equals negative 2y plus 6.
Z equals negative.
On the graph.
Oh, yeah, Z, yes, that's true. Thank you, thank you. Yeah, because I was sticking with the XY again, right? So, and this should be 13.6, same result. I mean 13.5.6. Now, we can solve this problem in a third way. In the same way that we did a projection onto the XY plane, we did it by means of projecting onto the YZ plane. We can set up the integral in a third different way, but in this case, projecting onto the XZ plane. I'm not going to do it, but I mean, if you want to do it on the wrong time, that's fine. Just so you can verify the result, you should get the same. So this is what happens with the surface integrals. So we get some freedom to projecting one way or another. And well, of course, the consequences is that one of the setups might give us an integral that's harder to evaluate than another setup. For example, the projection onto the xy plane. Check this integral, really easy to compute. As opposed to, well, it's not that bad, but it's more terms to take care of, right? But it's essentially a little more work, yes, right? So let's see what's next. So an application to find mass, like I was mentioning before, this f of x that we have, that it's no longer a single one that gives us the upper surface area on a surface. This time this f of x can represent some density function, and well, in this case that's going to help us find the mass of, in this case, a thin funnel in the shape of a cone, which equation is given, z equals to the square root of x squared plus y squared, and in this case within the limits 1 and 4. You'll see how is that going to work. You'll see the shape of it. It's going to look pretty familiar. So let me draw a cone in this case. Or actually, let me draw the planes first. So, so we have the plane, essentially z equals to 1 and z equals to 4. So 1, 2, 3, 4, 5. So that's the plane. Z equals to 1, 1, 2, 3, 4. And the plane, oops. Z equals to 4. And we're going to have the following cone. The following cone that looks like this. Looks like a Reese's chocolate, upside down, right? That's essentially the shape that we are integrating over. And now, careful, because in this case, we have a top larger circle and a bottom smaller circle. So when we look at the projection, we need to be very careful of how is that going to look like. So check this out. So let's look at the projection. That's going to be the shadow, of course, something like the shadow. And in this case, well, this unit circle, because, well, that's z equals to 1. That's the unit circle, and then a circle, in this case, of radius 4, which is going to look like this, all right? So that's our projection here, and let me shade. the projection. Well, I think I went over the boundary. All right. All right. So what do we have in this case? Well, well, number one, let's take the partial derivatives, and oh my God, that's going to involve some chain rule. That's the same as z equals to x squared plus y squared to the 1/2. And use a little chain rule. So the partial of the partial of z, not f, with respect to x. So that's 1/2 x squared plus y squared to the negative 1/2, and by mini chain rule, multiply by the derivative of the quantity inside of the parentheses, which in this case, well, the partial, since we're doing with respect to x, that's going to be 2x, and y squared, it's constant, so that just gets zeroed out, all right? We can do a couple of simplifications here, so cancel the 2's. Cancel these 2's, and we can send it to the denominator with positive exponent, x squared plus y squared to the 1/2, which is x over the square root of x squared plus y squared. And in the same way, the partial of z with respect to y, well, I'm not going to do the whole set, the whole work. It's going to be the same process, but instead of having an x in the numerator, that's going to be changed with a y. So that's a y over the square root of x squared plus y squared. Okay? Z. And well, let's set up the integral first. So number one, we have, well, in this case, the double integral of the function rho of x, y, z ds over the region S, over the surface S, and well, so that's the double integral of the function tan minus z, and that's the square root of the partial of z with respect to x, quantity squared, plus the partial of z with respect to y, quantity squared plus 1, and we call it, let's call it dA. I mean ds, dA for now, already, over s. All right, so let's substitute the partial derivatives. It's not going to be pretty because, well, and again, I'm going to do another substitution because notice this is a double integral. And this double integral, when we iterate it, whether this is dy dx or dx dy, we should be working with functions that are only functions of x and y. Did you see the z here? So we need to get rid of that z, or rather replace it with its corresponding function of x and y, which we have it here. So that's the double integral of 1 minus the square root of x squared plus y squared times the square root of the partial with respect to x squared, that's x over root of x squared plus y squared, quantity squared plus y over the square root of x squared plus y squared, quantity squared plus 1, and let me call it dA, because we're going to iterate this in a different way. And yes, this is madness right here, so we'll have, yes.
Would it be tan minus z?
That's what I meant, but not what I wrote anyway. Yep. 10. Thank you. Well, we would have to square this, and well, there will be some cancellations of the radicals with the powers. Yes.
If that's a 4, wouldn't it be just put some 4?
Yes, that's what we're going to do, because notice the region of integration. Notice our projection in the xy plane. It's circular. Well, it's an annular technically, but it's still circular anyway. So we're going to set it up by means of of the polar world, of course. So okay, so according to my work, to what I have over here in my notes, before setting this up, I'm going to, well, after simplifying all this madness inside of the radical, this will be simply, I know, the square root of 2. And that's dA over the region S. Now, indeed, polar coordinates. That's the double integral. I'm going to leave space for the limits now. So that's 10 minus the square root of the quantity x squared plus y squared. What is that in well, actually, I mean, that's simply r, isn't it? Yep. Because that'll be r squared, root of r squared. I mean, yes, all right? And either way, I mean, times square root of 2, r d theta. And well, the limits, the radius, let's look at this annular region and see how the radius varies between what and what? Anyone? Between 1 and 4. And because in this case, well, they're not telling us the first octant or the upper half. Well, they're essentially, in this case, we can assume it's the whole circle. So that's theta going between 0 and 2 pi. All right? So that's going to be from 1 to 4 and from 0 to 2 pi. And that's the integral that we can set. And well, that's just a polynomial integral, no big deal. Nevertheless, I have the answer to this. That should be 108 pi root of 2. So that's the mass of the funnel. That's the mass of this Reese's chocolate, if you will. All right? And let's see, the last part of this section, flux integrals. Well, we already did some flux integrals back in 17.4 when we covered, what was that, Green's theorem. But in this case, we did the flux integrals only for the 2D region, you know, only the 2D case in this situation. So let's look at a picture of how this flux integral actually depend on the orientation. So here is where normal vectors are going to come back and being put together with the surface integrals. Yes, sounds a little scary, but it's not. We're not going to be computing that. Remember that big normal vector back? No, we're not going to do that whole thing. Actually, well, when we do the derivation, there's a lot of simplifications with the formula. Okay, so unit vectors, but that could be unit, it doesn't matter. But the thing is, normal vectors are usually used to induce orientation. For example, grab your pencil and grab your paper. Think of this as your region to actually, the contour for this region. Well, so this is a plane, and we have this normal vector, this vector that is normal to the plane. Now, if this plane is, if this normal vector is pointing up, so if you grasp that vector, see the direction, my fingers, it's going in the counterclockwise direction of my paper, all right? If we do it the other way around, we would go in the clockwise direction. So we're going to use this orientation idea in order to find flux in one direction or the other. But here's the thing: recall that there's a few different kinds of surfaces. There's closed surfaces, and there's also open surfaces. Well, an example of a closed surface. A parallelepiped, a box, or a sphere, you know. And in that situation, for closed surfaces, we only think of the vectors pointing out of that surface. However, for surfaces that are open, like not that are closed, we have two options: either the vectors pointing outside or pointing inside, and that's going to make a whole difference when it comes to the orientation to determine the flux. And to calculate this, which is going to be similar to what we did using Green's theorem, but now we're going, instead of calculating over a planar region, we're calculating over a surface in this case, all right? Well, so let's formalize this. How do we find normal vectors? So we're given a function g of x, y, and we find the gradient. The gradient, we divide that by its magnitude to get those normal vectors. Well, how do we, well, in this case, we're going to define a special function because, well, recall that a surface is a function of two variables, a function g of x, y. We're not working with functions of three variables in this case. So I'm going to create another function here, big G of x, y. I'm going to turn it into a three variable function. And that function, so essentially, that's going to be z minus, I'm going to solve this equation and set it equal to 0 essentially, g of x, y, and set it equal to 0. And you might remember back when we covered this partial derivatives and we created some big g of x, y, z, set it equal to 0, so these two quantities are equal to each other. Essentially, we create this new function, all right? And we're going to take the gradient of that function. Well, so in this case, well, let me write the whole thing so it's read in one sentence for whatever reason. So, big G of x, y, z equals to z minus g of x, y. So the gradient, nabla of g, that's the partial derivative. Oh, that creates a vector. The partial derivative with respect x, which essentially is to differentiate the g with respect x times -1 because of the sign over here. And then the second component is the partial derivative of this function with respect to y. All right, it's g sub y. And then the derivative with respect to z, but in this case the derivative of z with respect to z is 1. And dividing by the magnitude, well, recall that the magnitude is just the square root of those components of the vector quantity square, right? And well, I intentionally left these negative symbols right here, negative signs, but recall that they just become positive, right, upon squaring them. Now, this is the element that we're going to use in this integrals. You might remember this double integral of f dotted with n ds. Well, it was actually dr back in Green's theorem. Well, when in the situation in which we had the planar region, now with a solid surface over here. That's going to be the normal vectors pointing out, well, depending on the direction of those normal vectors, depending on the direction whether we want to go counterclockwise or clockwise. And well, how do we get this integral? I know this is going to be a really nasty calculation to do, but check this out. So let me, actually, you guys might want to write this on the back of your page. And I'm going to create a blank page here. So number one, this double integral, big F dotted with n ds equals to those normal vectors, which in this case is, okay, so big F dotted with the normal vector, which we got to be negative g sub x minus comma negative g sub y comma 1 divided by the magnitude of this, which is g sub x squared plus g sub y squared plus 1 squared, which is essentially 1 times, okay, from the back of, okay, let me go back over here real quick. This is a surface integral, this is ds. Remember the element of surface? Remember how this element of surface that I'm going to highlight, this one right here, is going to become this madness right here. G sub x quantity squared, g sub y quantity squared plus 1 dA. And in this case, this is what I was talking about, how this cancel, and we don't have to calculate the magnitude of those normal vectors. So in the end, well, so, oh, again, what is this f? This big F is it's a vector f, g, and h. By the way, here is where I'm having a little issue, some issues with our textbook. Well, Because, well, this G that I have over here is just to represent the Y component of the given vector field. It's not the same G that we're using, so don't confuse it with that. Like I mentioned earlier in this chapter, if you look at other resources online or other textbooks, the components of a vector field are usually related with the uppercases M and P, or P and PQ, big letters in this case, to avoid confusion. But because this book doesn't use that notation, I will stick to these letters and just make sure that this G is not the same as this G. In fact, this is usually the surface that for which we take the partials for. Now, S, so that equals to double integral of S. I'm going to write this big F in terms of F, G, and, well, this is actually, let me write it as Z sub X, and let me write this as Z, replace it with Z sub Y, because, just to avoid confusion. So G, F, G, H, and negative Z, X, comma, negative Z sub Y, comma 1, dA. So let's do the dot product of these two vectors. Multiply component by component, and this is the double integral of S, F times, or rather, negative F Zx plus negative, or rather minus, minus G Z sub Y plus H dA. And this is the formula that we have in the definition box on the back side of your page, isn't it? So all we're doing is simplifying that horrible radical, and all we will have to do is find the dot product up to vectors. That's it. And yes, here it's right here. So let's look at one example. Find the flux of this vector field over the closed surface S equals to Z equals to 16 minus X squared minus Y squared, and Z equals to 0. So we need to have a bound over here, all right? We need to have a bound above or below 1. In this case, it's a bound below. So number one, what is it that we have? So this is a paraboloid. We see the X squared and the Y squared, and they're both negative, so it has to be an upside down paraboloid. So that's going to look like this, and hopefully I get to it's all right. All right, so that's the paraboloid. But in this case, there's something we need to discuss here. Number one, we're going to find the flux over the whole surface. That is, not only the curvy part, the part on the sides and top, essentially, but also we need to consider the bottom part. So we will essentially evaluate two double integrals. Well, yes, two double integrals. So number one, because in this case, check this out. For again, the convention for closed surfaces is that we have these normal vectors to point out of the surface, like this. And well, notice we have a bottom part over here. That bottom part has normal vectors pointing in the negative direction of K or Z, either way. All right. So we have a function Z, number one, for which we can already take the partials. So Z sub X, negative 2X, and Z sub Y equals negative 2Y. Let's set up the flux integral. In this case, the double integral of F dotted with N ds, and again, without even calculating those normal vectors, without even having to find, so notice the implication. This would imply to find the gradient of that function, normalize it, that is, divided by its magnitude, a lot of work, but in this case, we replace all this work with just this, just a simple dot product, all right? So, So that's going to be, okay. Oh, careful, because in this case we need to redefine. We can make some space over here. We need to redefine our vector field. In this case, what do we have? X plus y, that's fine. Plus y, that's fine. But did you see the third component? It's a z. We don't want z's in this case. We want only everything in terms of two variables, in this case, x and y. So we're going to replace this z over here, 16 minus x squared minus y squared. And well, that's going to be our f, and our nds will be simply this computation over here. All right, so this is going to be the double integral over s. That's x plus y comma y, 16 minus x squared minus y squared. And well, in this case is the vector for which we got the derivative. So in this case it's negative, well again this is negative, and careful with the signs, negative cx and negative zy. Check how we got zx, c with respect x to be negative 2x. But because of this negative, careful with those signs, that's going to be 2x, comma, negative, the derivative with respect to y, that's a negative, negative 2y, that's positive 2y, and comma, simply 1 in this case. And this is dA. And let's just do the dot product of this. Well, component by component, the quantity x plus y multiplied by 2x, that's going to give us 2x times x, that's 2x squared, plus y times 2x, that's 2x, and then plus y. Okay, let me highlight what am I multiplying. So x plus y times 2x to give us these two terms, all right? And then I'm going to multiply y with 2y to get 2y squared. And let me highlight these two, so you can see the result and you can see the connection between the two. And last but not least, let me choose a different color. So that's this madness here times 1, which is the madness here. dA. And this will be, let me highlight it so you can see where I got it from. All right, simplifying some terms, why not? That's going to leave us with the double integral over s of x squared. Hold on.
Your yellow part would be 2x squared plus 2xy.
Plus 2xy, that's true, right? 2xy. Yeah, I knew I had a mistake over here. All right, so that's going to be, okay, combining like terms. Okay, 2x squared right here minus an x squared, that's going to be 1x squared, right? X squared plus 2xy, and 2y squared minus y squared, that's another y squared, and plus 16. All right, and dA. So that's the integral that we have to evaluate. However, let's observe our region of integration, in particular, the projection onto the xy plane. So I'm going to do, as usual, notice the base is circular, isn't it? The base is circular, so and in this, oh come on, that's not what I meant to do. Yes. So that's a circle, and in this case, well, that's the circle 16, x squared plus y squared equals to 16, isn't it? Which is a circle of radius what? 4. Radius 4. Okay, again, did you see the pattern here? We're integrating over a circular region. What's the best thing to do here? Convert to polar, all right? So So r varies between 0 and 4. And theta, well, in this case, they're not telling us anything about, oh, the first octant or half of the circle. No, so it's everything in this case. So that's 0 to 2 pi. And, well, what's next? Just write down, oh, all right. So, convert to polar. Converting to polar, see how x squared plus y squared equals r squared. R squared plus 2xy, that's 2r cosine, r sine, plus 16. And the differential part, that's r dr, or the element of area, r dr d theta. And let's just write the limits of integration. We already got them from the projection into d. That's 0 to 4 and 0 to 2 pi. All right. And well, after evaluating this integral, we should get 384 pi. Now, this is only the first part. All right. This is only the first integral, but don't worry, the next one is going to be pretty quick. You'll see. All right, so what do we have? Okay, so notice the other function, the function for the bottom part. All right, let me label this as a 2. Number 2. In this case, the bottom of this paraboloid is given by the equation of the circle, or rather the equation of the plane. It's not even an equation of the circle because see how this base right here, the one that I shaded in blue, actually extends throughout the whole xy plane. But isn't that really z equals to 0? Right? Are you guys following me here with this? Okay, so check why is this it's going to be like really short to do, because in this case we're going to work with z equals to 0. What's the partial derivative with respect x? What the partial derivative with respect y? So let's set up the double integral. That is the double integral over, well, in this case I'm going to call it over r. That's f n ds. And in this case, we simply compute the double integral over r of x plus y, which is the vector field, x plus y, y, 0, because again, check this out. Our original vector field is x plus y, y, z. Again, we want to get everything in terms of x and y. What is z in this case? Isn't it 0? Because it's the plane, the xy plane. And that's the partial derivatives, 0, 0, 1. In other words, let me label what did I do here. So that's z with respect x and z with respect y. Just so when you get back to see your notes again, you can see where are these really coming from. All right, so that times dA. Okay, let's do the dot product of these two vectors. So what's x plus y times 0? 0. What's y times 0? What's 0 times 1? The whole integral is 0. All right? Now we need to name the total flux. Total flux, this will be 384 pi plus 0. Well, that's just 184. So it could have been the case that in the surface below there would have been some flux in this case, all right? But not for this particular vector field that we were working. Maybe for a different vector field there would be. All right? So this finishes this section. We still have some time. Let's discuss the next section. I don't know what happened with the copy machine. It printed twice as many. I said 25 and it printed like 50. So let me mute it real quick.